Now it's time to talk about Bronsted-Lowry and bases. Okay? Under the Bronsted-Lowry definition, a base accepts a hydrogen ion. Now this really expands our definition of a base. The hydroxide ion is still a base because it's got that wonderful oxygen with 3 lone pairs of electrons. It's very good at accepting a hydrogen ion, but also means things like ammonia with the nitrogen that has a lone pair of electrons can act as a hydrogen ion acceptor, as can the fluoride ion, the oxide ion, the sulfide ion, the cyanide ion. Hint, these are all anions that are conjugates of weak acids. Okay, so now under the Bronsted-Lowry definition, we can expand out what we think of as a base, and we can talk about strong bases and weak bases. Now, a strong base is a salt that contains a hydroxide ion and dissolves up well in water. The alkali metal hydroxide, sodium hydroxide, potassium hydroxide, lithium hydroxide are all strong bases. Salts that contain oxide ions and sulfide ions that dissolve up well in water are strong bases. So sodium oxide, sodium sulfide, lithium oxide, lithium sulfide. And hydroxide, oxide, and sulfide containing salts of calcium, strontium, and barium. So barium hydroxide, calcium oxide, strontium sulfide are all strong bases. Notice our list of strong bases is not that big. Weak bases, that's ammonia, amines, which are organic molecules that have a nitrogen that have a lone pair of electrons. Let me show you some amines. So we know ammonia. If I substitute one of the hydrogens for a CH3 group, so if I had CH3NH2, looks like this. Lone pair of electrons on the nitrogen, that's a base, a weak base. I could have CH3 taken twice NH. As long as I've got that hydrogen with a lone pair of electrons, it's an amine and it's a basic molecule. Okay? The last category are anions that are conjugates of weak acids. So think about that chart that I showed you that had acids and their conjugate weak bases. All those anion conjugates are weak bases. So the anions that are conjugates. Okay? So that means that we have a much more expanded list of bases in the Bronsted-Lowry definition. Weak bases then fall into 2 main categories, what we call molecular bases or neutral weak bases. Neutral meaning they have no charge. Ammonia and the amines are the molecular bases. They contain a nitrogen that has a lone pair of electrons on it. Example, NH2CH3. Okay? But here's a list of neutral or molecular weak bases. This is not by any means all of them. This is just a small list. So we have diethylamine, dimethylamine, methylaniline, ammonia, pyridine, aniline. Okay? And notice they have Kb values. So let's talk about writing the reaction of a molecular weak base with water and talk about what Kb is. Now, if I have ammonia and I react it with water, ammonia is going to be our base, water is going to be our acid. Ammonia picks up a hydrogen ion, it becomes a hydronium ion. Water gave up a hydrogen ion, it becomes a hydroxide ion. So base, conjugate acid, acid, conjugate base. Okay? If I have NH2CH3, it goes through the same process. It's going to accept a hydrogen ion from water to become NH4CH3 plus. The hydrogen is written with a nitrogen because that's where it went, and I made a typo there. Let me fix that. Okay, so it should be NH2CH3 plus water going to NH3CH3 plus and a hydroxide ion. The hydrogen that was gained goes to the nitrogen. Okay? Now, in general, we can say that a neutral weak base, a molecular weak base, will react with water to give me Hb plus and OH minus. And the equilibrium expression is Hb plus times OH minus over B concentration. And we give that a special designation Kb because it's a base ionization. I took something that was neutral and I made an ion out of it. So it's a base ionization reaction. Okay? Now, all the problems that we could do for a weak acid, we could also do for a weak base. Before we do any of those, though, I want to talk about the anion weak bases. These are conjugates of weak acids and would be introduced into solution in the form of some kind of salt. The cation, the salt, can be thought of as a spectator ion for the interaction of the anion, the weak base, with water. Fluoride ion, ClO minus, the carbonate ion, the nitrite ion, for example. So ClO1 minus reacts with water to give me HClO and OH minus. So to go from ClO1 minus to HClO, I had to accept a hydrogen ion. Go from water to hydroxide, we had to donate. So weak base, acid, weak acid, base. Fluoride ion with water gives me HF plus OH minus. So that our generic here, nope, won't let me scroll up. Okay, that went a little far. I hate this screen. Okay. Let's see what this sucker's doing. Okay. Let me get this back in line, guys. I'm sorry. So there's our generic. Our anion, A minus plus water, gives me HA and the hydroxide ion. So Kb is HA times hydroxide ion over A minus. For each of these reactions, we can write equilibrium expressions, and they are called weak base dissociation constants. Okay, some people call them weak base ionization constants. It's not really a dissociation in the true sense of the word, so I like ionization constant better. Okay? Now, let's look at some anions and how they act as bases for a minute. Okay? When you go and you look for tables of Kb values for anion weak bases to get their Kb values, you're not going to find them. And that's because of a conservation of kind of print material. Okay? There's a relationship between the Ka of a weak acid and the Kb of its conjugate base. So if we looked at, for example, HF as a weak acid and the fluoride ion is its conjugate base, okay? Here's a reaction. HF plus water goes to H3O plus F minus, aqueous, aqueous, aqueous liquid. Okay, and there's the Ka is 6.8 times 10 to the minus 4. Here's the reaction of conjugate base with water. The fluoride ion plus water going hydroxide ion and HF. Aqueous, liquid, aqueous, aqueous. If you add those two reactions together, notice that the fluoride ion is going to cancel out, and the HF and the HF are going to cancel out, and you get water plus water gives me hydronium ions and hydroxide ions. This is the auto-ionization reaction with water, and it has a Kw of 1 times 10 to the minus 14. We know when we add two reactions together to get a third reaction, you just have to multiply the 2K at the equilibrium for the two reactions you were given to get the third, which means that for an acid-base conjugate pair, Ka times Kb equals Kw. So if you can look up the Ka for the weak acid, you can determine the Kb for its conjugate base. Okay? All right, now, let me stop right here. Okay, guys, we're doing acid-base chemistry, and we're talking about bases, specifically weak bases. And the two categories of weak bases are the molecular weak bases, sometimes called neutral bases because they have no charge, and the anion weak bases, which are the conjugates of weak acids. For the conjugate acid-base pairs, okay, the Ka times the Kb for a conjugate acid-base pair always has to equal Kw. Now, all of the problem types that we could do for weak acids, we can do a similar problem type for a weak base. Given pH and initial concentration, we ought to be able to calculate Kb. Given initial concentration in Kb, we ought to be able to calculate pH. Now, we might have to use a Ka for a weak acid to find the Kb for its conjugate base. So let's do a couple of molecular bases, amines, and then we'll move on and do some anion weak bases, okay? Now, when we're dealing with a weak base problem, and we're determining Kb, trying to find Kb from an initial concentration of the base and pH, we first have to write a balanced chemical equation. We have to write the Kb expression, okay? You're probably going to need to do an ice chart and then determine the hydroxide ion concentration using the following. 14 minus pH equals POH, and then hydroxide ion constant equals 10 to the minus POH, okay? Note that this is X in your ice chart, so it's also the constant, not only is the concentration of the hydroxide ion, but it's your concentration of Hb plus, and you can use it to find your concentration of your initial weak base to begin with. So let's start out with a 0.100 molar pyridine solution that has a pH of 9.12, and we want to find the Kb. So, okay? So we're given that we have pyridine. And the pH is 9.12, and we have a 0.100 molar initial concentration. Now, you may not know what the structure of pyridine looks like. It doesn't matter. I'm going to use the generic B plus water is going to give me Hb plus plus OH minus, both of those aqueous. So that the Kb expression is HB plus OH minus over B concentration. Do my ice chart. Okay, this is 0.10000 minus x plus x plus x, x, and 0.100 minus x. Okay, now I'm going to start out by getting POH. That's going to be 14.00 minus 9.12. So 14 minus 9.12 is 4.88. So our hydroxide ion concentration at equilibrium is going to be 10 to the minus 4.88, which is 1.3 times 10 to the minus 5. So that means X is 1.3 times 10 to the minus 5. So hydroxide ion concentration is 1.3 times 10 to the minus 5. HB plus is 1.3 times 10 to the minus 5. And if I subtract that from 1.1, I still get, rounding off to 3 significant figures, 0.1. So if I plug in my KB expression at 1.3 times 10 to the minus 5 times 1.3 times 10 to the minus 5 all over 0.100, so I get a KB value of 1.7 times 10 to the minus 9. Not too bad. Now, the only thing that's different from stuff we've done in the past is having to do this step to get POH before we do anything else. Okay? Now, let's do a problem where we want to find pH. In other words, we want to find concentrations at equilibrium. We're going to look at problem 16.12 on page 713 in your text. So flip over to 713. Come on, book, work with me here. Okay, the problem reads, find the hydroxide ion concentration and the pH in a 0.33 molar methylamine solution. So we're given 0.33 molar methylamine. That's CH3NH2. But if you didn't know what methylamine was and I didn't give it to you, you could just use B, go generic. Okay, we want to know hydroxide ion concentration and pH. Now, methylamine is one of those that's found in the chart in your book. Methylamine has a KB of 4.4 times 10 to the minus 4. On exam, of course, that would be given to you, or I'd be giving you a table. So we want to go through the same thing again. CH3NH2, aqueous, plus water, liquid, going to CH3NH3 plus OH minus. Both of those are aqueous. The KB expression is going to be CH3NH3 plus OH minus over CH3NH2 concentration. Okay. We do our ice chart. CH3NH2, CH3NH3 plus, OH minus, This is 0.33, this is 0, minus x, plus x, plus x. Notice these ice charts start to get very repetitive in the acid-base chapter. So 0.33 minus x, x and x. Now, if I plug into my KB expression, I get 4.4 times 10 to the minus 4 is equal to x times x over 0.33. Now when I look at this, there's about a 1,000-fold difference here. So I'm going to assume that 0.33 minus x is approximately 0.33. It's pretty close, but I'm going to assume anyway. If I do that, I get 4.4 times 10 to the minus 4 is equal to x squared over 0.33. So 4.4 exp4 negative times 0.33, take the square root. So when I solve, I get x is 0.022. Now I'm going to check. 0.022 divided by 0.33 times 100%. Ooh, I get 6.6%. When I get a percentage like that, it says, you can't make an assumption. Okay, so I'm going to have to dig down and do some heavy duty work. So you guys have all this written down, so I'm going to have to do the long stuff. Okay? So I can't make the assumption. So I'm going to have to work this out the long way. So 0.33 times 4.4 exp4 negative gives me 1.5 times 10 to the minus 4 minus 4.4 times 10 to the minus 4x is equal to x squared. So I get x squared plus 4.4 times 10 to the minus 4x minus 1.5 times 10 to the minus 4 equals 0. So x is going to equal a minus 4.4 times 10 to the minus 4 plus or minus the square root 4.4 times 10 to the minus 4 squared minus 4 times 1 times the minus 1.5 times 10 to the minus 4 all over 2. So let's do it. So I have minus 4.4 times 10 to the minus 4 plus or minus 0.0245. I'm overkilling it on significant figures. Now I'm going to run the numbers one more time. Nope, that's it. All over 2. Now there's two possible solutions. One where I add and one where I subtract. So 0.0245 minus 4.4 exp4 negative divided by 2. One solution is 0.012. Okay? 0.4 exp4 negative. And the other one is a minus 0.013. A negative x can't happen. We can't have a negative concentration. So that one's out. This is our answer. So our pH, our hydroxide ion concentration here at equilibrium is 0.012. Our pOH is the negative log of 0.012, which is 1.92, and our pH is going to be 14 minus 1.92, which is 13.7 14 minus 1.92. Yeah, that looks better. Hit something wrong. 12.08. Now, on the exam, I could ask you what concentrations of everything are at equilibrium. You just take your X back to your ice chart and you can do it. Okay? So there's an example of going from pH to the KB, going from KB to a pH. Okay? So there's an example of both of those. Now let's take on the anion weak base option. Now just to remind you, anion weak base A minus plus water gives me HA and hydroxide. There's the KB expression. Okay? Now when we're dealing with a conjugate anion base, okay? A weak base, it is the conjugate of a weak acid and it's an anion. You're probably going to find the Ka for the weak acid, and they're in your book on page 695, and you're going to have to use that to get the Kb. Remember, Ka times Kb has to equal Kw, and that pKa is just the negative log of Ka, and pKb is the negative log of Kb. Okay? So we're going to look at a problem. We're going to look at problem 16.14 on page 716. That's just a couple of pages over. Okay? Now, when we look at the problem, let me get the board clear here so we've got some room to work. When you're looking at the problem, it says, what is the pH of a 0.25 molar sodium acetate solution, C2H3O2? So we want to find the pH, and we're given, we have a 0.250 molar NaC2H3O2. Now, first thing that should jump out at you is you've got that sodium ion in the sodium at the beginning of the formula. So the sodium we're going to ignore. We got to concentrate in on this. We have C2H3O2 1 minus. This has to be an anion weak base. The sodium ion here is a spectator ion. Okay? So I need to find the conjugate of that to start out with. So if we look back on page 695, I'll pull up 695 here. Okay, let me flip over so that you can see the book. Okay, so we're looking for that formula acid. Okay? Now, if you look right here, acetic acid, HC2H3O2. So if I just replace that H with a sodium, that's what I've got. So what we've got is the acetate ion, which is the conjugate of acetic acid. So the Ka for acetic acid, HCH3O, okay, HCH3O2, has a Ka of 1.8 times 10 to the minus 5. So, let me show you. I'm sorry. Guys, I keep forgetting I got to slide my camera. So there's the acetate, acetic acid. See the HC2H3O2? That's acetic acid. Its conjugate is the acetate ion. So if we took away the hydrogen there, okay, and there's its Ka value. All right, so I've got the Ka there. That means that Kb is just going to be 1.00 times 10 to the minus 14 divided by our Ka, 1.8 times 10 to the minus 5. So 1 exp 14 negative divided by 1.8 exp 5 negative. So that gives me Kb of 5.6 times 10 to the minus 10. Okay? Now, our reaction is C2H3O2 1 minus plus water. Water's a liquid. This is aqueous. Reacts to give us HC2H3O2 aqueous plus hydroxide ions aqueous. That's acetic acid. Okay? Our Kb expression is going to be HC2H3O2 times hydroxide ion concentration all over C2H3O2 1 minus concentration, acetate ion concentration. Now let's do our ice chart. So, CH3O2 1 minus, HCH3O2, hydroxide ion 0, 0, and this is 0.250, minus X plus X plus X. On these acid ice charts, that's always going to be your change line. So 0.250 minus X, X, and X. Now, look how small Kb is. There's no way I can't make an assumption. I am going to assume 0.250 minus X is approximately 0.250. If I do that, then I get 5.6 times 10 to the minus 10 is equal to X times X over 0.250. I just plugged in from the equilibrium line to the Kb expression with my assumption. If I solve this for X, I get X to be 1.2 times 10 to the minus 5. I can just look at that and say my assumption is good. Because if I subtract that from that, I'm not going to notice it. If I subtract that from 0.250. So our hydroxide ion concentration here is 1.2 times 10 to the minus 5. Our POH is a negative log of 1.2 times 10 to the minus 5. So 4.93. So our pH is 9.07. Remember, these are basic solutions. The pH has got to be greater than 7. Okay? All right, time to move on. With the discussion here of anion weak bases, I need to talk about salts and the fact that a salt doesn't necessarily have to be neutral. I mean, the last salt we looked at was acidic. Okay? So sometimes acids and salts can be acidic or they can be basic. So I want to introduce you first, think about some cation weak acids and talk about transition metals for a moment. Okay? Now, what do I mean by cation weak acids? Well, if we think about ammonia, which is a neutral weak base, or something like methylamine, CH3NH2, when they react with water, they produce NH4 ammonia plus the ammonium ion and a hydroxide ion. And this guy reacts with water to produce CH3NH3 plus and the hydroxide ion. Aqueous, 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 liquid, liquid, aqueous, aqueous. Let's look at this guy and this guy. If that's a base, then its conjugate is a weak acid. So this is a weak acid. This guy is also a weak acid. These are cations that are acidic in nature. Any conjugate of an ammonia or an amine is going to give me a cation that is a weak acid. Okay? Now, those aren't the only weak acid cations out there. A surprising group of weak acid cations are transition metal ions. Okay? Something like iron 3+, or copper 2+, or cobalt 2+. These guys are actually acidic. And you look at me and you go, how? Well, these guys actually, when they dissolve in water, okay, they form metal complexes. The iron 3+ will sit in the middle of 6 water molecules. And I'm doing a very crude drawing here. Now, there's also another water molecule out here and another water molecule behind. So you get an Fe3+, 6H2O. Well, actually, they go Fe, 6H2O, and the whole thing has a 3+ charge. These are called complexes. Okay? The oxygen, because it's so electronegative, and the iron being +3 and being so tiny at this point, is able to pull electron density toward it. It actually forms what's called a coordinate covalent bond with the oxygen. This is the first time we've talked about a metal-related something forming covalent bonds. But the iron 3+ forms coordinate covalent bonds with the oxygens. Now that starts pulling even more electron density away from those hydrogens. Whee! The iron 3+ acts like a very electronegative element, but it's an ion. So we've pulled electron density away. Okay? When that happens, and this guy bumps into a water molecule that's not part of the complex, we get an acid-base reaction going on. Now I think your book does a much prettier job than I can do. Yeah. So let's look at it. Okay? Now aluminum will do this too. So there I've got the aluminum in the middle of the complex. Okay, electron density is being pulled toward the aluminum. A nearby water acts as a base, and I get the formation of the hydronium ion, and then I get one of the waters that was part of the complex losing its hydrogen. Okay, so I get aluminum H2O5 OH2+. But this complex acts as a weak acid. So transition metals, especially those on row 4, and things like aluminum, have an acidic characteristic because of their complex ion behavior. What I'm trying to work toward here is that a salt solution could be acidic, could be basic, or could be neutral, depending on the nature of the cations and the anions that are in solution. Okay? So, a salt is formed during the reaction of an acid and base. Usually a neutral salt is formed when a strong acid and a strong base react in a neutralization reaction. So a strong acid like sodium hydroxide reacting with a strong base like hydrochloric acid gives us HCl and water. The sodium ion, okay, all the alkali metal ions are neutral. All of the halogen anions, except for fluorine, the fluoride ion, are neutral. So I have neutral, neutral, and water. It's a neutral salt. Okay? So our neutral cations, sodium, potassium, rubidium, cesium, magnesium, calcium, strontium, barium. These, when they're combined with hydroxide ion, are considered to be strong bases. Neutral anions are like chloride, bromide, iodide, the chlorate ion, the bromate ion, the chloride ion, the nitrate ion. They're all considered neutral anions. So sodium chloride, potassium nitrate, calcium bromide, cesium perchlorate are all considered neutral salts. Okay? When a weak acid and a base react, the relative strength of the conjugate acid-base pair in the salt determines the pH of the solution. The salt or salt solution the salt solution could be acidic, basic, or neutral depending on what the anions and cations are. So acidic cations would be things like the ammonium ion, ions made out of amines, the aluminum ion, the lead ion, the tin ion, and transition metal ions. You also have the hydrogen sulfate ion and the bihydrogen phosphate ion, which are anions which are actually acidic. Basic anions are things like the fluoride ion, the acetate ion, the nitrate ion, the bicarbonate ion, the cyanide ion, the carbonate ion, the sulfide ion, the sulfate ion, the hydrogen phosphate ion, the phosphate ion, the oxide ion. Okay? So when you look at these, you have to look at them and you have to determine whether each ion is neutral or not. For example, ammonium chloride. The ammonium ion is acidic, the chloride ion is neutral, so an ammonium chloride ion would be acidic. Sodium ion is neutral, the acetate ion is basic, so sodium acetate would be a basic solution. Okay? So I just enclosed another table to give you a little bit, some more examples of things that would be acidic, things that would be basic, based on the anion and the cation. So notice if I have a cation of a strong base and the anion of a weak acid, I end up with something that is basic, okay? If I have the cation of a strong base and the anion of a polyprotic acid, I'm going to get something that's acidic. All examples. Now problem 16.16 on page 720 in your text gives us some examples of, well, I'll let you work that on your own. That's just you talking yourself through it. So I'm not gonna do that in my lecture. I'm gonna leave that up to you guys to do on your own. Okay. Now, let's talk about water, okay? Because when we talk acid-base chemistry, we're usually talking about what's happening in water. And notice that water is amphoteric. Whenever I dissolve an acid up in water, okay, it reacts to produce hydronium ions. When I dissolve a base up in water, we're going to get hydroxide ions. If I dissolve HCl up in water, which is what we call a strong acid, it 100% ionizes in water to hydronium ions. And then I have a hydronium ion solution. So what this tells us is that the strongest acid molecule that can exist intact in water is the hydronium ion. And the strongest base particle that can exist in water is the hydroxide ion. Any acid that's stronger than the hydronium ion is 100% converted to hydronium ion in water. Any base that is stronger than the hydroxide ion when dissolved in water is converted 100% to the hydroxide ion. This is called the leveling effect for water. No matter what strong acid we dissolve in water, the strongest acid particle that can exist intact is the hydronium ion. Same thing is said for a base. No matter what strong base we dissolve in water, the strongest particle that's basic that can exist in water is a hydroxide ion. So, one of the things that always drove Arrhenius quite crazy was that all strong acids look the same in water. What he had to ultimately realize is really what he was getting the same acid. The acid was the hydronium ion. He just wasn't aware of that. So to get relative strength of strong acids like HCl and HBr and HClO4, you have to dissolve it up in something that's not water. And they usually dissolve